All right, guys, so this video is going to be covering the notes for 7.2. This will be covering similar polygons. So to start off, we want to talk about what is a polygon. A polygon can be described as a shape with 3 or more sides. And so now that we understand what a polygon is, we need to talk about what does it mean for them to be similar, right? So we're looking at this section right here. What are similar polygons? Similar polygons can be described as polygons that have the same shape, but not necessarily the same size. So let's look at an example of what something like this might look like. So for polygons to be considered similar, they need to be the same shape. Well, if I draw these two polygons, we can see that both of these are the same shape. They're both triangles. So these two would be considered similar. Now, last semester, you've kind of heard the word shape and size before, right? We looked at what do I call two figures that are the exact same shape and the exact same size? We said that this was congruent. And so one thing to make note of here is, well, we want to understand the difference between similar and congruent. And I want y'all to kind of listen to this part very carefully. For two figures to be congruent, they have to be the same shape and the same size. Now that's different than figures to be similar, polygons to be similar, they just have to be the same shape. So up here, these are similar but not congruent. And the part in red, well, they are congruent, but these would also technically be similar as well, right? Remember the criteria for polygons to be similar. It really just means that they have to be the same shape. And in red here, well, they're both triangles, so they would be similar as well. So the key focus that I want you to take away from this section of the notes is going to be the following. For polygons to be similar, these two things have to be true. Corresponding angles have to be congruent, and corresponding sides have to be proportional. So as we look at this, let's kind of review some of the vocabulary that we have here. The word congruent, when we're talking about angles, it basically just means that they're going to have to be equal, right? And so corresponding angles are going to have to be equal if those polygons are similar, right? And the word corresponding, this just means matching positions. Let's fix this here. So corresponding just means matching. So matching positions. So angles in matching positions have to be congruent. And corresponding sides here have to be proportional, right? And so now we want to talk about what does proportional mean, okay? Proportional means that the ratios are equal. We looked at this yesterday in the notes. And so we'll get a better understanding of what this looks like as we start to look at some examples a little later on in the notes. But for right now, this part's extremely important, okay? You need to understand that if polygons are similar, then corresponding angles are congruent, and that corresponding sides are proportional. So now let's look at what is the symbol that we use for similar. The symbol that we use for similar is going to be this right here, okay? That squiggly line. So anytime you see that symbol stands for similar. And so we can see that right here. What we have written right here, this is known as a similarity statement. And so as we read this, we can understand here that, well, A, B, C, D, this little symbol we're saying here means similar. So the way we read that is A, B, C, D is similar to E, F, G, H. And so if these A, B, C, D, E, F, G, H is referring to the picture above, if these two shapes or polygons, if they are similar, then that means what we just stated above has to be true, that the corresponding angles have to be congruent and the corresponding sides have to be proportional. And so let's talk about those corresponding sides being proportional. What this means is that for corresponding sides to be proportional, then our ratios have to be equal. And that's what we're seeing here. Notice that we have four ratios, four fractions here that have all been set equal to each other. And we're going to see here that AB is this side, it corresponds to EF right here. So that's how they're building and setting this up. BC corresponds to FG, right? So that's why they set those over each other. And it's really just kind of a matching game here. GH corresponds to CD. So CD and GH correspond to each other. And then Lastly, we have the sign on the bottom, which would be AD. I'll actually use a different color here. AD corresponds to EH. And so one thing you just want to be very careful of is pay attention to the order, okay? The order here, here's A, B, C, D. They're putting those sides on the top of all of the ratios. And they're putting the sides of E, F, G, H, that polygon, they're putting all of those on the bottom, right? So just be consistent with that order. I could also flip that around to where you could also write it like this as long as you're consistent. I can choose to start with the polygon on the right first. So I can start and basically write this as EF over AB. That would be equal to FG over BC. It's equal to GH over CD and EH over AD. So pretty much the same thing as long as you are consistent. So depending on how you write that first ratio, make sure that you're being consistent here. So what I mean by that is notice that the parts that I'm writing on the top, I'm starting with, I got EF, FG, GH. I'm putting this one on the top. So you can be writing it either way. Totally up to you. All that we ask is that you guys are consistent. So let's kind of start to look at some examples here now of what some questions might actually look like. So it says, name the congruent angles and the proportional corresponding sides from the figure below. So if we take a look at the figure below, I have two polygons. Specifically, I'm looking at two triangles, right? And the questions here, the blanks that we're filling in is asking you, angle A is congruent to, well, let's look at the picture. If you notice here, angle A has one ring, right? That angle A would be congruent to which angle in the second triangle? Well, it'd be congruent to the one that also has one ring, which would be angle D. So those are congruent. Then we could take a look at angle B. Angle B has two rings, so that would be congruent to the angle with two rings in the second triangle, angle E. And then lastly, we have angle C. Angle C would be congruent to angle F because they both have three rings. And so now what we're basically using is the definition from the beginning of the notes. What we're seeing here is look at the angles in the triangles. Are my corresponding angles, are all of them congruent? The answer here would be yes, right? A is congruent to D, B is congruent to E, and C is congruent to F. Based off of our definition from the beginning of the notes, right here, we said that for polygons to be similar, the corresponding angles have to be congruent. As we look at the example we were just on, are the corresponding angles congruent? Well, yeah. If those corresponding angles are congruent, then they are similar. Then the triangles themselves are similar. And if the triangles are similar, then we can write a similarity statement, right? And so we're going to jump ahead to filling in the blank right here where it says similarity statement. We're going to write this in as triangle ABC. Well, just look at the order in which it's written. What does A correspond to in the second triangle? Well, A corresponds to D. And then going in order here, B corresponds to, looking at the picture, E. So ABC is similar to triangle DEF, right? And so that would be our similarity statement. Okay, so again, for you to be able, and we'll look at this more in detail later on in the notes, but for you to be able to determine whether triangles are similar or polygons in general are similar, you need to show one of two things. Either that the corresponding angles are congruent, which we just showed right here, or you can show that the corresponding sides are proportional, which we'll see here in the section below. So now what we're going to take a look at is filling in the rest of the blanks. Okay, if I look at this here, AB, you can complete this blank here by either looking at the picture or by looking at the similarity statement that we wrote. Take a look here, and we'll explain it both ways. AB is the first two letters. What does AB correspond to in the second triangle? Well, it corresponds to DE. So AB corresponds to DE. And if I mark that in the picture, we see that that makes sense. AB and DE go together because those sides connect the red and the green angle in both triangles based off of how we color coded it. Same idea here. If I look at the next blank, BC, well, BC connects the green angle and the blue angle, so corresponds to this. This is where the color coding sometimes might be helpful. So BC would be to EF. And then lastly, we have CA. Okay, CA would be to, well, this bottom side here, but you want to be very pay careful attention to the order here. It said CA, right? So blue angle to red angle. Blue angle to red angle would be FD. So this would be FD. You could also just look at it from the statement that we wrote earlier. This is CA, so CA would be FD. It works the same way. So either way that you want to write this, if you have the similarity statement, you can always rely on that to figure out what is corresponding. All right, so now let's take a look at what a similarity ratio is. So to determine proportionality, the ratios of the corresponding side lengths need to be consistent. And for them to be proportional, they need to not only be consistent, but they need to be equal as well. So if we take a look here at the numbers that we have here, there's a lot of information kind of presented in front of us. Let's kind of make sense of what it's saying, right? So it's telling you that if you're going to be consistent, the way that you can do this is you'll notice that the consistency is what we did a little bit earlier. So you'll notice that the numbers that I'm putting on top are coming from triangle STU. The numbers that I'm putting on the bottom are coming from triangle XWV. And so now the way that we're going to set this up is we don't have a whole lot of information, and our job right now is to figure out what are my corresponding sides, right? My corresponding sides, we can do this by looking at the size of each side in the triangles individually. So if I look at the yellow triangle, you'll notice that 3 represents the smallest side. What is the smallest side in the pink triangle? 9, 12, and 15. The smallest number here is 9, right? So that's why they're writing that first ratio. They're writing it as 3/9. We do the same thing with the medium side. If I look at the yellow triangle, my medium side is 4, and my medium side in the pink triangle is 12, right? So I got 4/12, right? And this is what we mean by let's be consistent. Once you write that first ratio, you need to be consistent. The first ratio that we have written here is 3/9. I put the 3 on top. That means that, look, all the numbers I'm putting on top are coming from the yellow triangle. And so next we'd be looking at 5, which represents the largest. So largest over largest would be, starting with yellow, the yellow triangle, this would be 5/15. And so this is known as a similarity ratio. And so for us to be able to say that, are these proportional? For these to be proportional, okay, all of these ratios, we have 3 of them here, they must be equal, okay? The only way for this to be proportional or similar, okay, if I want to check, are these proportional? Ratios, for that to be said, the ratios must be equal. So let's look at these ratios individually. I have 3/9. The way that we can tell whether or not ratios are equal is by simplifying, okay? If I simplify 3/9, okay, this gives us 1/3. I'm checking here, are all of these ratios equal when simplified? And if you're struggling with simplifying fractions still, remember that you can type these fractions into the yellow calculators and it'll simplify it for you. So we're not going to spend a whole lot of time simplifying here. I'm just going to tell you what it simplifies to. 4/12 simplifies to 1/3. 5/15 also simplifies to 1/3. So notice how all of these ratios here happen to be equal, right? I have 1/3, 1/3, 1/3. So when all of the ratios are equal, then that means it's proportional. So if it's proportional, okay, then that means that the triangles are similar. So the key takeaway from this section of the notes that I really need y'all to understand is that whenever you are checking to see whether the triangles are similar, you need to focus on the ratios. Are the ratios of the corresponding sides proportional? Okay, so to determine proportionality, ratios need to be consistent and equal, right? And so that's what you're checking for. And I'm going to give you guys kind of a little flow chart that you can add to your notes so that you can better understand how to answer these questions, okay? And what it is that I'm trying to tell you guys. So we're going to use this flow chart to determine whether or not triangles are similar. So if you look at example 1, it says determine if the pair of triangles are similar, okay? The first thing you're checking for is, are the corresponding sides proportional? If you say yes, then that means it's similar. If you say no, then that means it's not similar. Okay? And remember, for things to be proportional, okay, that means that all the ratios must be equal. So let's kind of look at an example now just from what we will actually expect to see like on a homework assignment or on a quiz or a test. So what we'll look at here is we'll look at the two triangles that we have, right? Now, you'll notice that these triangles, unlike the previous example, they don't have any letters for the angles, right? So I'm still going to highlight though, and I'm going to kind of just try to follow the same order here, right? I'm going to continue to use the same colors. So I'm going to put the numbers for my yellow triangle on top and the numbers for my pink triangle on the bottom, right? So I'm basically doing this, yellow over pink. So let's write this here. That's going to be how I'm setting up my ratios. So if I start here, let's go ahead and begin with my smallest side, right? My smallest side in the yellow triangle is 3. That corresponds to the smallest side in the pink triangle, which would be 16. So I can write this ratio as 3 over 16. We're checking to see, is that equal to the other ratio of the corresponding sides? If I look at the medium side here is 4. Medium side in the second triangle is 18. So I got 4 over 18. And then we have to check now, is that going to be equal to the largest over the largest, which here we're looking at, my largest side is 5 here, my largest side here is 20. So 5 over 20. So what we're checking for now as we're going through that flow chart, are all of my corresponding sides proportional, right? I got my ratios for all corresponding sides, my small over small, medium over medium, large over large. We need to check now, are we going to get the same value? 3 over 16, I'm going to simplify each of these ratios. 3 over 16 cannot be simplified any further, so it stays the same. 4 over 18, though, simplifies to 2 over 9. 5 over 20 simplifies to 1 over 4. You'll notice here that these ratios, when simplified, they're not equal. So if they're not equal, that means that no, they're not proportional. Now, if they're not proportional, then that means that they're not similar. So to answer the question, determine if the triangles are similar, the answer would be no, they're not similar. They're not similar because those corresponding sides are not proportional. And that would be the reason why you would put not similar. So let's look at the next problem. Next problem, we're looking at two triangles again, okay? I like to just kind of make habits here, so you'll continue to see me kind of use the same colors for these problems typically. So I'm going to go ahead and follow the same format, my yellow triangle and my pink triangle. So when I set up my ratios, I'm going to do yellow over pink. So same idea here. And now that y'all understand kind of how this works, we're just going to do this kind of really quickly all on one triangle at a time. Let's look at the sides of my yellow triangle. 10 is the smallest, 12 is the medium, 16 is the large. If I look at the other triangle, then we're looking at 5 is the smallest, 6 is medium, 8 is the largest. So as I might write the ratios, then let's just set this up really fast. So small over small would be written as 10 over 5. Medium over medium would be 12 over 6. Large over large would be 16 over 8. And so what we're going to do now is we're following that same flowchart again, okay? Again, I'm writing that flowchart here separately so that we can kind of circle it and not get confused with what we had earlier. We need to check, are these corresponding sides proportional? Yes or no? If they are proportional, you say yes, then that means that the triangles or whatever polygons you're looking at are similar. If you say no, then that means that they are not similar. So as we look at this here, 10 over 5, that simplifies to 2 over 1. 12 over 6 simplifies to 2 over 1. 16 over 8 simplifies to 2 over 1. So you'll notice here that, well, all of these ratios here are equal. So if all of the ratios are equal, then that tells us that those corresponding sides are proportional. Now, if they're proportional, then that means that they have to be similar. So for this example, the answer to the question, determine if the pair of triangles are similar, the answer would be yes, they are similar. Okay, so hopefully that gives you a better idea of how do I determine whether two triangles are similar or not. You're checking to see, are those corresponding sides proportional? Next, we're going to talk about something known as the scale factor. Okay, so the scale factor, whenever you have two polygons that are similar, the ratio of the lengths of two corresponding sides is called the scale factor, represented with the letter K. So scale factor, what I really need y'all to understand, and it's not really stated here in the notes, but that's okay, because this isn't the emphasis of what we're learning, but it is kind of worth mentioning here. Try to write this. This is not writing how I need it to, but scale factor, this basically tells you the change in dimension. And this will hopefully make sense here as we look at the previous example, okay? So I'm going to erase this so that we kind of have a blank canvas to look at in the previous example. So in the previous example, what I'm trying to tell you guys is that the scale factor tells you the change in dimension for similar figures. So we've already determined, okay, look, we already said that these two triangles are similar, right? So the scale factor will tell you the change in dimensions. Remember that we labeled 10 as the smallest and 5 as the smallest. These sides are corresponding. These triangles are both similar, okay? What happened is that they changed in size, right? So what's happening? How are they changing in size by? Well, what's happening is that, reading this from left to right, what we're basically doing is we're multiplying by 1/2, right? Half of 10 is 5. If I look at the other values, well, look at the medium. What's half of 12? Half of 12 is 6, right? So as soon as you understand what that scale factor is or that change in dimension, you can start to figure out what those other side lengths are going to be in the event that we're ever missing one. And so similarly over here, look at 16. My scale factor here, my change in dimension, is that all of the side lengths in the first triangle are being cut in half, right? So half of 16 is giving us 8. Right, and so that's the real importance behind scale factor. Now, there's a very specific order that you have to follow for scale factor. And this is a vocabulary word that we learned earlier on this school year. Scale factor was something that we used whenever talking about dilations. And so this isn't something that we're going to really, quiz or test you over, but this might be something that you might see like on something like a DLA or something. You need to understand that all dilations create similar figures or similar polygons. So what that means is that transformation that we did at the very beginning of the school year, dilations, remember what that did is that made a figure larger or smaller, right? So the shape didn't change, but the size did. So all the dilations that we've looked at in the beginning of the school year, those were actually examples of similar polygons. And so what we're going to look at now is, well, let's review. How do I find the scale factor? The way that you find the scale factor is by using this formula that I'm going to circle here in blue, okay? This formula, with an emphasis on this part right here, your scale factor is found by just taking new divided by old. You're going to take the corresponding sides of two polygons, and you're going to start with the new and divide it by the old. That will tell you the scale factor, which again is the change in dimension, right? And so we're going to have essentially a majority of the time, we're going to have two possibilities. Either these polygons are going to be enlarging or they're going to be reducing in size. If you have an enlargement, you'll notice that it's an enlargement whenever your scale factor K is greater than 1. You have a reduction or it's reducing in size whenever your scale factor K is in between 0 and 1. Typically, this will be a fraction or a decimal, but that fraction or decimal must be between 0 and 1. So if I had a decimal like 2.4, that doesn't mean it's reducing. That 2.4 is technically greater than 1, so that would be an enlargement. So let's take a look at example 2. Okay, let's kind of start looking at finding scale factor. So it says, use the figure below to answer the following questions. It says, identify the scale factor from triangle CBA to FED. The order matters here, right? So now it's up to you to determine which one is the new one, which one is the old one, okay? When it says from that represents your old. That means that you're starting with triangle CBA. And that then means that the new one here would be triangle FED. So as we look at this, let's look at some corresponding sides here. All right. So if I look, and you can really use any side, you don't have to do all three like we did earlier. You just have to pick one side to find the scale factor. So I'm going to just pick 10. Okay. 10 in the first triangle, CBA, what does that represent? The small, medium, or large? Well, if you look here, it represents the smallest side. So what side is that going to correspond to in the new triangle, FED? Well, it's going to correspond to the smallest side here, which in this case is 12. So these are corresponding. And so now our job is to just find the scale factor. If I want to find the scale factor, remember scale factor is found by taking new divided by old. Well, in these corresponding sides here, my new would be coming from triangle FED. So it's going to be 12 over the old, which is triangle CBA, which would be 10. So my scale factor here is 12 over 10, which we now need to determine, well, is that scale factor a enlargement or a reduction? Scale factor of 12 over 10 can be simplified to, this would be 6 over 5 or 1.2. So I'm writing it in both fraction and decimal so that you can better understand, well, is that scale factor, is it greater than 1? Well, 1.2, yeah, it's bigger than 1, so that tells us we have an enlargement. You could also just tell by looking at the numbers. I mean, if I look at starting here, okay, if I start here and end here, look at the numbers. What's happening between 10 and 12? It's getting bigger. It's enlarging. All right, and so now let's look at the part B of this example, okay? I'm going to erase this because now part B kind of changes the order on you guys a little bit. So kind of the same problem, same numbers, but now it says identify the scale factor from triangle FED to triangle CBA. The from part, that represents your old. That means that CBA is my new. So if I take a look here, I mean, I can use the same numbers, right? We understood already that my smallest side here was 10 in this triangle. Smallest side here is 12, right? So we understand that these are corresponding. If I want to find my scale factor, then we're just doing, again, new divided by old. Except in this one, my new is coming from CBA, right? So here, this represents my new. Here, the second triangle represents the old. So my new here, I'd be writing then 10 on the top. And now 12 was going to be my old for this problem. 10 over 12, if I simplify that, 10 over 12 is going to end up, you can divide the top and bottom both by 2. So we get 5 over 6. Okay. This will be a really, really kind of long decimal. If you get a really long decimal, we prefer that you guys just leave it as a fraction. This will end up being approximately 0.8333333. So when the 3 goes on forever, you just write a little bar on top. That means 3 repeating. So our scale factor here, you see that it's a fraction. It's a 5 over 6, or as a decimal, approximately 0.83 repeating. And we'll notice that, well, is that bigger than 1? The answer to that is no. That means we are looking at a reduction. What's happening is if I start here from if I go from old to new, so in other words, if I start here, what's happening? It's getting smaller, right? 12 is getting smaller and becoming 10. And so that essentially is how scale factor works. Please pay very careful attention to the order. You find your scale factor, again, by taking new divided by old. And so we'll look at kind of a few more examples and we'll finish up here. So in example 3, it says, are triangles JKL and triangle MNO similar, right? Remember that, and I know we're talking about a lot of different things here, but let me erase this so this doesn't get kind of confusing or in the way. But for triangles to be similar, that means corresponding angles are congruent. And that also means that corresponding sides are proportional. So to justify our answer, we're going to look at the corresponding angles. Are my corresponding angles congruent? Let's take a look here. If I look at my angles, well, if I look at angle L, okay, angle L is 40, right? What would angle L be congruent to? Well, the other angle in the second triangle that has 40, angle O. So angle L is congruent to angle O. Next, we're looking at the 32. There's not a specific order you need to go in here. If it's not specified for the order, you get to choose. 32 degrees is angle J. That would be congruent to 32 degrees in the other triangle, angle M. And then lastly, if I look here at the 108, that angle right there of 108, they're both the same. That means they're congruent. So angle K is congruent to angle N. And so now, like we said earlier, for triangles or polygons in general to be similar, the two things have to be true. Corresponding angles are congruent and corresponding sides are proportional. If I show that at least one of those is true, that is enough information to say that they're similar. Okay, so right here, that list of corresponding angles being congruent, that is enough information to say that these triangles are similar. Okay, so that's plenty of information to say, hey, these triangles have to be similar. Now, let's kind of prove that by showing that the corresponding sides are proportional, right? My corresponding sides here, if we look at this, I'm just going to match them up by highlighting them so I don't just put a whole bunch of different colors on here. Well, I'm going to put a whole bunch of different colors, but just so that it's less confusing, hopefully. If I look at the triangle on the left, the smallest side is 2.7. The smallest side in the second triangle is 5.4. If I look at the medium side here is 4. Medium side in the other triangle is 8. And then lastly, my largest side is 5, and my largest side here is 10. So we're basically setting this up with how we have it color-coded. Yellow over yellow is going to check to see, is that congruent, or it should say equal, to be honest, and we'll fix that here. Is that equal to the ratio given by pink over pink? So now we have to decide, what do I want to start with? Okay, what I want to start with here, personally, I read from left to right. So whenever I do this, I'm going to make sure that I'm putting the numbers from triangle JKL on top and the numbers from triangle, the second triangle here on the bottom. And so now I want to make sure that I match the order up. Angle, if I start with J is in green, that angle. So it matches up with M. And then the next letter is K. K matches up with the red angle, so N. And then my last letter is O. So that's going to be, again, what we meant by wanting you guys to be consistent. So if I look at yellow over yellow, again, I'm starting with the triangle on the left, JKL. So I got 2.7. So we're looking at 2.7 over my other yellow, 5.4. Pink over pink, I got 4 over 8. Green over green, I got 5 over 10. Right? If I were to simplify all of these numbers, and like I said earlier, these should not be congruent symbols. These should be equal signs. We're checking to see, are these equal? We're going to check, what does it simplify to? 2.7 over 5.4. I'm going to write this down here and I'll erase it later, but this simplifies to 1 over 2. 4 over 8 simplifies to 1 over 2. 5 over 10 simplifies to 1 over 2. All these ratios are equal, so that means that the corresponding sides are proportional. And if they're proportional, then that means that triangles are similar. So that would be another way that we can justify it, okay? You can show both, but you technically only really need to show one or the other. You can either show that the corresponding sides are proportional like we just did here, or like we did earlier, you could also just show that the corresponding angles are congruent. Okay, so now we're going to actually look at how exactly are we going to start to use this information to begin finding missing sides or missing angles. So let me erase this, okay? And hopefully you got this copy down. I'm just going to erase it so that, it's not as confusing. And so what I'm going to do now is I'm going to zoom in, okay? I'm going to zoom in so that we can just see this a little bit closer. And, okay, hopefully not that much. Okay, that's about as much as I can zoom in here. So, example 4. Now we're going to use what we've learned to start finding missing information. It says find the value of x if triangle ABC is similar to, remember that symbol right there means similar, to triangle GHJ, right? So here is where we're going to kind of use everything that we've learned and kind of start to put it together. I need to find x, right? So I need to obviously use this side that contains x. That side is represented by BC. What does BC correspond to in the second triangle? Well, it's the second and third letters, so it's going to correspond to the second and third letter HJ. So these two guys go together. That means that I can write yellow over yellow as a ratio, in this case, x over 16. And it tells us already that these triangles are similar, so I know that these ratios have to be equal for these corresponding sides. So now you get to pick. You just pick another one of those sides. I'm going to just choose this side, which is 12. That is BA. So BA. BA is the first two letters, so that corresponds to HG. Here, by looking at the picture, it seems pretty obvious which ones are corresponding, but not every picture is going to be really easy to look at like that. They might rotate it, they might flip it. So I always suggest, like I'm using in this example, look at the similarity statement. So now if we look at pink over pink here, then we're doing 12 over 8. Okay, so we set up our ratios and we were consistent, right? So I had this on the top, okay? So I started with, I'm going to just call this figure P, and we'll call this figure Q. So, I mean, I'm using the same kind of consistency here. I'm putting the numbers from figure P on top and the numbers from figure Q on the bottom, right? And so we've got this ratio set up now, and this is really the whole purpose of yesterday's notes. Now, how do I solve an equation like this? We solve equations like this by cross multiplying, right? So if I multiply diagonally here, then we can have a way for us to find x, right? So if I look at 8 times x, then we have 8 times x is equal to whatever 16 times 12 is. And as we work this out, 8 times x is 8x. 16 times 12, if we multiply that out, we get 192. Now, if I divide both sides by 8, we get that x is equal to 24. And so what I always tell my students is after you find x, reread the question, make sure that you've answered it. Well, example 4 said find the value of x. We found it. It's 24. All right, so next we got example 5. It says use the properties of similar polygons to determine if the following, if triangle JLM is similar to triangle QST. Okay, so pretty much same idea here. So if I want to find all the information listed below, then we can go ahead and start with the first thing I see is Y. Okay, Y is going to be found on side JL. So JL corresponds to QS. So these two guys are corresponding. So if I want to set up an equation here, then we can at least begin with 3y minus 2, putting that over the corresponding side of 5. Now, we understand that these triangles are similar, so all the ratios have to be equal, the corresponding ones. And so now we need another corresponding side to work with so that I can cross multiply. It wouldn't make sense for us to use the x, because then I would be involving a second variable, and that makes things a lot more difficult to solve. So instead, I would suggest choosing this side. 4 would be JM, which would correspond to QT. So these two guys go together. So it'd be equal to 4 over 2. And there's our setup. Now all we have to do is just cross multiply. Okay, I'm going to go through this process a little bit faster because you should be hopefully familiar with solving equations like this based off of yesterday's notes. So we got 5 times 4, which is 20, is equal to, I guess let me color code this. We got 20 is equal to, when you multiply 2 times 3y minus 2, I like to always just put that in parentheses so that I don't forget to multiply this out correctly. So if I multiply this out, what we get here then is 20 is equal to, well, 2 times 3y is 6y. 2 times negative 2 is negative 4. From here, you add 4 on both sides. What we get here is 24 is equal to 6y. If 24 is equal to 6y, then when I divide by 6, we get that 4 is equal to y. So, answering this question here, y is equal to 4. The next blank that we have here is JL. Well, JL is given by 3y minus 2. Well, if JL is 3y minus 2, we just found y is 4, so plug it in. 3 times 4 minus 2 gives us 12 minus 2. So JL is 10. JL is 10. Next we have, they're asking us for Z. Okay, and they're asking us for Z. What you'll notice here is Z is found right here with this angle, angle L. So as I look at this, what corresponds to angle L? angle S. Okay, so these two are corresponding. And now you need to pay careful attention to what we've been kind of repeating throughout the notes and the very first thing in the beginning of today's notes. If two triangles are similar, if polygons are similar, the corresponding angles are congruent. So if my corresponding angles are congruent, what does that mean? Corresponding angles congruent. Congruent means that these corresponding angles have to be equal to each other. So we can say here that 2z has to equal 48. If I solve this, all we have to do is just divide by 2. That gives us that z has to equal 24. So z is 24. The measure of angle L, well, if I want to find angle L, we just said that the corresponding angles are congruent. So if L corresponds to S, they both have to be congruent. That means that they both have to be 48. So they both have to be 48 degrees. And you could plug in the 24, multiply that by 2, you're going to get the same answer. All right. So again, takeaway from this is to solve for missing sides, you're going to cross multiply. You need two ratios equal to each other. To solve for missing angles, if the triangles are similar, remember that corresponding angles are congruent. So these corresponding angles will just be equal to each other. And then we'll finish up with the last section of the notes. All right, so we're looking at perimeters of similar polygons theorem. Okay, so this part really take away from this is if two polygons are similar, ratio of their perimeters is equal to the ratios of their corresponding side lengths. And so what this means is, in this case, this isn't going to make a whole lot of sense with the letters, but this basically is this part right here is the perimeter of NKLM. This right here is the perimeter, and I'm going to erase this here in a little bit so it doesn't get in the way later, but this is the perimeter of SPQR. So the ratio of the perimeters is equal to the ratio of the corresponding sides, right? So we can understand that essentially what that means is if two polygons are similar, then all of the corresponding sides are proportional, and that would apply to the ratio of the perimeters as well. So this would be KL over PQ would be equal to LM over QR. That would be equal to MN over RS, and that would be equal to NK over SB. Right? Just looking at all those, if it's similar, then all those corresponding sides have to be proportional, meaning that all of the ratios have to be equal. So we're going to kind of see how this works and the connection behind it. Okay, I'm going to erase this really quickly so that it doesn't get confusing or in the way later. So as we look at example 6, then it says use the diagram to answer the following questions. I'm going to speed through this because I know this video is already running extremely long. So part A says quadrilateral CBAD is similar to, well, based off of how it's drawn, we can kind of understand what is going to be the corresponding parts here. If I went CBAD, then it would be GFEH. So it's similar to GFEH. It says find the scale factor to create quadrilateral EFGH. So this is another way to kind of word these types of questions. Scale factor. Remember that was new over old. If we are creating quad EFGH, quad just means quadrilateral, four-sided shape, then this creating means that that's going to be the new one. So all we have to do really here is pick two corresponding sides. Well, the only corresponding sides that I have values, both of them in, would be these right here. So what we're seeing here for this one, the new is EFGH, the one on the right. So this would be written as 10 on the top and on the bottom 2.5. Now if we simplify this, 10 over 2.5, that divides out and gives us 4. So the scale factor is 4. And so remember that the scale factor, yes, that's new over old, but that tells you the change in dimensions. So that means that, from here to here, what am I doing? I'm multiplying by 4. 2.5 times 4 is where we get the 10 from. We can use that information to help us find the other missing values here in a little bit, right? So let's take a look here at the next part C. It says find the scale factor now to create ABCD. So creating this one means that now this is the new one. Okay, so if I'm doing new over old, that kind of changes things for us. So I'm looking at the same corresponding sides in yellow, 2.5 and 10, but now the new one is going to be coming from quadrilateral ABCD. So the 2.5 now is going to go on the top, 10 is going to go on the bottom. If you simplify this, what you end up with is 1/4. So my scale factor is 1/4 for this. Now, the more that you understand about scale factor, the easier it's going to make your life. Now, we learned in the last problem how to kind of find these missing pieces here, right? So the way we find these missing pieces, part D says find the values of x, y, and z, right? If I want to find x, right, x here corresponds to 16, right? So if I want to write this as a ratio to solve for x, then our ratio would end up being x over 16, blue over blue, is equal to 2.5 over 10. If I cross multiply here, 2.5 times 16 is going to give us 40. 40 is equal to 10 times x, which is 10x. Divide both sides by 10, you get that 4 is equal to x. Okay, if I want to find y, you can kind of do the same thing here. Solve for y, you can set up your ratios, or you can use the scale factor to your advantage, right? My scale factor here, if I want to create quadrilateral EFGH, so if I'm creating this one like this, my scale factor tells me the change in dimensions. So it's going to be us multiplying the sides by 4. Well, what's 3 times 4? 3 times 4 is 12. So this should be 12. And I'm going to prove it to you by solving it the same way we just did earlier. BC corresponds to FG. Let's pretend that we didn't know it was 12. So if I set this up, this would be 3 over y is equal to, I'm going to use the same yellow over yellow, 2.5 over 10. Cross multiplying here, we got 2.5y is equal to 3 times 10, which is 30. Now if I divide this out here, if I want to solve for y, divide both sides by 2.5. When you start working with decimals and stuff like this, it's totally fine for you guys to, use a calculator and just be 100% sure. But if I divide 30 divided by 2.5, you're going to get 12. So this kind of just goes and shows that you can use the scale factor to find these missing values. Just make sure that you show your work in some way, shape, or form. So next we'll look at z. Sometimes it's pretty obvious, sometimes it might not be. So for z, some of you guys might see what the answer could be by using the scale factor. Or if you don't, that's okay. You can always just set this up as a proportion, right? So this z corresponds to 5. So setting this up, I have z over 5 is equal to, again, I'm using yellow over yellow, 2.5 over 10. Cross multiplying here, 5 times 2.5 gives us 12.5. And that's equal to, well, 10 times z is 10z. Now if I want to solve for z, divide both sides by 10. If you divide both sides by 10, what you get is 1.25. It's equal to z. Okay, and so at that point we found all of the values of x, y, and z. Okay, moving on with the notes, it says find the perimeter of quadrilateral ABCD and quadrilateral EFGH. So now that we know the length of each side, what I'm going to do here is I'm going to label all of the values that we got here. So for this one, this was 12 for y, right? Z, we got 1.25. It's 1.25. And x, we got 4. So if I want to find the perimeter, let me zoom out a little bit here so we can see the whole thing. If I want to find the perimeter, so right here, it says find the perimeter of quadrilateral ABCD and quadrilateral EFGH. Quadrilateral ABCD, the perimeter would be us adding up all the sides. So this would be 4 plus 1.25 plus 3 plus 2.5. So if we add those up, we have 4 plus 1.25 plus 3 plus 2.5. That gives us a perimeter of 10.75. So my perimeter of quadrilateral ABCD is 10.75. Next, I'm looking at the perimeter of quadrilateral EFGH. So again, I'm adding up all the sides here, a little bit easier, numbers are a little nicer. We got 5 plus 12 plus 10 plus 16. 5 plus 12 plus 10 plus 16 gives us a perimeter of 43. So my perimeter here is 43. Okay, so if I want to, answer the next part, it says find the ratio of the perimeters, right? The ratio of the perimeters is just going to be, the first perimeter over the second one, or vice versa. So I can write this two ways. I can write this as 10.75 over 43. Or I can write this as 43 over 10.75. Okay? And so what you'll notice here is that if we simplify these, okay, so the ratio here, we're writing it down, but we want to simplify it. Okay, again, if you want to simplify something, easiest way to do this is in the calculator. This ratio right here is going to simplify to 1 over 4. The other one in red would simplify to 4 over 1, which could be understood to just be basically 4. Now, those are the ratios of the perimeters. Now it's asking you in part F, how does the ratio compare to the scale factor previously found? So, in other words, look at what we got for the scale factor. What do you notice? I mean, I did these in the wrong color, but that's okay. But what do you notice about these scale factors and the ratio of the perimeters? They're the exact same. The ratio of the perimeters is the same as the scale factor. So you can write this here. Ratio of the perimeters is the same as the scale factor. Okay, and that's really the key takeaway from this example. What we'll look at is a warm-up question tomorrow in the notes or the following day, so that you can see what a problem like this would look like and how this theorem would be helpful. Okay, but that's going to be the end of the notes. I know that this set of notes ran long, but this is the foundation behind this entire chapter, so I wanted to make sure that we went through things thoroughly. If you have any questions or you find yourself still struggling, as always, please make sure to reach out to your teacher for tutorials.